Welcome students. Now we are going to see the next operation, that is shaping. Okay, so in shaping operation we are having the tool which is put on the beam, okay, which is reciprocating, and this is the workpiece of, say, this is the length L and this is the width B, okay, and it is reciprocating. So shaping operation is basically used for machining of the flat surfaces, and here we are using the quick return mechanism. This is the crank, okay, this is the connecting rod, and the crank is moving with the constant speed. And here we are getting two strokes, one is forward stroke and one is return stroke. So during the half of the revolution we are getting the forward stroke, and the remaining half revolution of the crank we are getting the return stroke, okay. So here of course the crank is having the constant speed, but we are having different velocities. For the forward stroke we are having different velocity, and for the return stroke we are having two different velocities. So how this we are going to get? By this quick return mechanism. So here the mechanism that we are using here is Whitworth quick return mechanism. So which is the one of the inversion of single slider crank, isn't it? So to get this return stroke with high speed, we are having this Whitworth quick return mechanism here, okay. So here the tool is reciprocating and the feed is given to the work, isn't it? So here intermittent feed is provided. Please remember here the intermittent feed, by using which mechanism? The ratchet and Powell. The ratchet and Powell mechanism is used to get this intermittent feed. That is, in the forward stroke, the tool is going to remove the layer of the material. That is, it is a cutting stroke where the cutting is going to happen, and during the return stroke it is coming back with the high speed. During return stroke no cutting, so that is why it is ideal stroke. So it is ideal stroke. If no cutting is there, then it should be the fastest stroke to minimize the machining time, isn't it? So here forward stroke, whatever the cutting velocity required for the cutting operation, say the VC is the optimum cutting velocity that we have for the forward stroke, and return stroke, as there is no any cutting, so it should be the fastest stroke to minimize the machining time. Now see, we are having, if the shaping machine and the workpiece are get vertical, okay, so if these two are in the vertical position, then the operation is known as the slotting operation or slotting machine, isn't it? This is shaping machine. If it is vertical and a workpiece also vertical, then it is the slotting machine, isn't it? And here see, the work table is given the feed and tool is reciprocating. This is the shaping operation. So when the width of the workpiece is very large, so if you use only single shaping machine, then definitely time required for the machining will be very high. So in that case what we are doing, instead of one tool, more than one tool or many number of tools we are using for removing the material from the work surface. And here the tools are reciprocating while the workpiece is rotating, okay. So workpiece is going in front of the tools and the feed is given to the tools, then this operation, okay, this operation is nothing but the planning operation. So planning operation, here the workpiece is rotating and feed is given to the tool. Okay, large size workpieces get machined by using this planning operation. In planning operation we are using more than one tool or many numbers of tools. Okay, now see in the shaping operation. So shaping operation, say one revolution of crank, how many strokes we are getting within one revolution of crank? One is cutting stroke plus another is return stroke. So that is why, see, in a single revolution of crank we are getting these double strokes. That's why it is also known as number of double strokes. Okay, number of double strokes. Now if say VC is our cutting stroke velocity or simply the cutting velocity, and VR is your return stroke velocity. Okay, if we are having the length of the workpiece L or length of the stroke is L, okay, and the time required for the cutting stroke will be TC. TC is what? Time required for cutting stroke, and TR is a time required for return stroke. Then what is the total time? Or total time is what? Time required for cutting stroke and time required for return stroke. So totality, what I can say, the time required for the double stroke, because these two strokes are going to happen in a single rotation of the crank. So the time required for the double stroke, okay, kitna lagega? So time for the forward stroke, that is cutting stroke, plus time required for return stroke. Isn't it? Now see here, if L is the length of the stroke and VC is the cutting velocity and TC is the cutting time, then tell me what will be the cutting speed or velocity I can write? Distance L divided by time, cutting time TC, isn't it? So here, and of course here we are using the Whitworth quick return mechanism. So there will be the quick return ratio, say small m is the quick return ratio, which is equal to either cutting velocity by return velocity or return time by cutting time, because now we know velocity is inversely proportional to the time. So either I can have this value of QRR in terms of velocity or in terms of time, and if of course this will be less than 1, because here return velocity is maximum or the cutting time is maximum. That is why it should be less than 1. Now see, if this M is equal to R by TC, then can I write this TR is equal to M times TC? Yes, I can write. So put this value of TR here, that is TC plus EM into TC. Take TC common. TC is the cutting time into bracket 1 plus M. Isn't it? Which is equal to what? Time required for the double stroke. Now what is TC? TC is what? From this equation, can we have TC is equal to cutting time is equal to length of stroke divided by cutting velocity? Yes, that is L divided by VC into 1 plus M. This is the time required for the double stroke. And of course the velocity will be in what? Meter per minute. So convert it into millimeter per minute. If the L it is in millimeter, then it will be L into bracket 1 plus M divided by 1000 VC. Now if this is the time required for double stroke, can we determine the revolution of the crank or the crank RPM? How to find out crank and RPM? Crank revolution per minute will be, it is 1 upon time required for the double stroke, that is 1000 VC divided by L into bracket 1 plus M. Okay, so very simple. See, we are getting the formula is very, very important. This is very important formula. This is also very important formula. Okay, now we got the value for time required for the double stroke. Now how many number of double strokes are actually required to complete the operation to get it done? Say, what was the diagram? So this is my length of the workpiece and see, this is the width. So definitely tool is reciprocating from this given position and workpiece is having the feed, isn't it? The workpiece coming front of the tool, isn't it? So this is the width. So what will be the total number of double strokes are required? Double strokes are required to complete this entire workpiece, to complete the operation. How much? That is width of the workpiece divided by the feed, isn't it? And here feed is what? S is the feed in millimeter per stroke. For every stroke, how much feed that is given to the workpiece, so that the entire width of the workpiece get completed, isn't it? So this is nothing but B divided by S. So this will be in millimeter divided by mm per stroke. So you will get, these are the strokes required to do this operation, isn't it? Now here if you are getting the total number of double stroke, that is B upon S, and you know that the time required for the double stroke, is how much? That is L into bracket 1 divided by 1 plus m, L into bracket 1 plus m divided by 1000 times cutting velocity. If this is time required for a single double stroke and these are the number of double stroke, then for finishing this entire operation, tell me how much time you will require. That is time required for machining, time required for completing this shaping operation, for completing the operation. How much? This will be this time required for the double stroke into number of double stroke, isn't it? So time required for the double stroke is how much? L into bracket 1 plus m divided by 1000 VC into number of double stroke. कैसे calculate करोगे? B upon S. So we can get the formula. So T, machining time for the shaping operation, is equal to L into B into bracket 1 plus m divided by 1000 times cutting speed into the feed, that is S, which is in minutes. Okay, so this is how we can get the various formulas in the shaping operation, and of course many times the question asks for the machining time calculation on the shaping. Okay, we will see when we are going to solve the numericals. So this is the shaping operation. Thank you.